I welcome you all to this problem solution series in digital electronics. I am solving the problems from the book Digital Design by Maurice Mano and Michael Celletti. So in this video, I am solving the problem number 6.24 from the chapter number 6. The problem is design a counter with T flip-flops that goes through the following binary repeated sequence. That means this counter will go through this count sequence of 0, 1, 3, 7, 6 and 4, and after 4 it will again go to 0 and it will repeat because it is given that it has a repeated sequence. Okay, then we have to show that when the binary states 0, 1, 0 and 1, 0, 1 are taken to be don't care conditions, the counter may not operate properly. So in the first case, we will consider the binary cases, that is 010, that is 2, and 101, that is 5. The counter do not operate properly. That means these two conditions are missing from these counting steps. So we have to show that there is some problem, and then we have to find out a way to correct the design. So first of all, what we will do, we will make the state table according to this given repeated binary sequence. So in the state table, we will have the present state, that are suppose A, B and C. Okay, then suppose we have next state. Suppose they are A of n plus 1, B of n plus 1 and C of n plus 1. Suppose these are the next states. Okay, and then we have to find out the respective flip-flop inputs for these T flip-flops. Okay, so here we'll find out flip-flop inputs. This FF means flip-flop inputs. They are TA, TB and TC, because here we can see that we have a maximum count of 7. Okay, so 7 is nothing but 111. Okay, so we can design this counter through 3-bit input or 3-bit flip-flops, or with 3 flip-flops we can design this 3-bit counter. So present state can take any values. Okay, so we will write down all the combinations using 3 digits. So here we'll have 000, 001, 010, 011, 100, 101, 110 and 111. We will find out the next state as per the given conditions. That means whenever we have 0, it will go to next state 1. Whenever we have 1, it will go to the next state 3. And from 3 it will go to 7, and from 7 it will go to 6, and from 6 it will go to 4, and after 4, if 4 is there in the present state, it will go to 0. So let me write down. So first of all, we have 000. So from 0 there will be a transition to 1. Okay, so 001. So here we have 001. So from 1, now the present state is 1. So next state will be 3. So 011. Okay, now we have 2. The value 2 is not given in this sequence. So for 2, we will consider it is the don't care conditions. So for 3 present state, the next state will be 7. So we will have 111. And for this 4, the next state is 0. So it will be 000. And this is 5 present state. So the next state will be don't care conditions because it is not present in the given sequence. So next we have this is 6. So from 6 there will be a transition to 4. So it is 100. So from this 7 we will have to go to 6, that is 110. So now we have got the next state values as per the given sequence. So for T flip-flop, next state output Q of n plus 1 is equal to T XOR Qn. That means the next state output is the XOR operation between the present state output and the input T. Okay, so whenever we have 0, to get the next state 0, so that means there is no change. So here we have 0. Okay, that means 0 XOR 0. So next state is 0. So similarly for this one, 0 and 0 again. So here for TA we have to consider this first column and this fourth column. Okay, so for 00 we have TA is equal to 0. That means these TA values you can find out using the excitation table, or you can think in the reverse order of this equation, characteristic equation. So for 00 again we'll have 0 input. Next we have 0 to don't care. This don't care condition we do not know, for it might be either 0 or 1. So here also we will write don't care condition. So for 0 to 1, this TA should be 1. So 1 0, this will be 1. And again we have don't care condition. So we'll write here don't care. We do not know. That means this don't care means we do not know what are the inputs, and we also do not know about the nested output. So next we have 1 1. So it will be 0. That means no transition. 1 1, it will be 0. Now let us find out the TB value. So for TB we have to compare the second column and this fifth column. So 0 0, it will be 0. 0 1, so it is 1. So don't care we have, then don't care right here. Then we have 1 1, so it will be 0. 0 0, it will be 0. So don't care. Then we have 1 0, so it will be 1. 1 1, it will be 0. Next we have to compare this C column with the next state of C column. Okay, so here we'll find out the TC value. So here we'll have 0 1, so it is 1. So 1 1, it is 0. Don't care, here we'll have don't care again. So 1 1, it is 0. So 0 0, it is 0. 0 don't care, here we'll have don't care. And 1 0, it is 1. So here we'll have 0 and 0, it will be 0. So we have got this state table for the counter. State table for the counter. Now from this state table we will find out the expression for TA, TB and TC. Okay, so for that we have to make the Karnaugh map for TA, TB and TC, and accordingly we will find out the equations for TA, TB and TC. The K map for TA. Okay, so for TA we will have a 3 variable map because we have 3 input variables A, B and C. So A, B and C. So here we'll have to fill up with the TA values. So TA value is 0 0 don't care 1, 0 0 don't care 1. Then we have 1 don't care 0 0, 1 don't care 0 0. So how we can combine? So this will be one combination, this is the second combination. So here we'll have TA is equal to, so from this term we'll have A bar B, A bar B, plus from this combination we'll get A B bar, A B bar. So this is nothing but A XOR B. Okay, so we have got the expression for TA. Now let us make the K map for so here we have to fill up with these TB values. So 0 1 don't care 0, 0 1 don't care 0. Then we have 0 don't care 1 0. So how we can combine? So this will be one combination, this is the second combination. So TB is equal to, this is B bar C, B bar C plus this is B C bar. Okay, so this is nothing but B XOR C. So we have got the expression for B. Okay, now we'll make the K map for TC. So here also we'll have a 3 variable map. So here we have to put the TC values. So TC values are 1 0 don't care 0, 1 0 don't care 0. Then we have 0 don't care 0 1, 0 don't care 0 1. So this will be one combination and this will be the suppose second combination. Okay, so TC will be, from this term we'll have AC plus from this combination we'll get A bar, this is C bar. So we can write here A XOR C. Now let us make the state table for the unused state. So here we'll have present state, suppose next state, and here we have suppose TA, TB, TC. Here we have 2 unused states. They are 0 1 0 and 1 0 1. So the next state values for this respective value, we have to first of all find out this TA, TB and TC using the equations of TA, TB and TC. So we know that for TA it is A XOR B, for TB it is B XOR C, and for TC we have A XOR C. This TA will be A XOR B, so 0 and 1 it will be 1. So here also 1 and 0 it will be 1. Next we have TB. TB is B XOR C. So B XOR C. So 1 and 0. So it will be 1. Again we have 1 and 0 and 1. So it will be 1. Next we have TC. TC is A XNOR C. So 0 and 0, so it will be 1. So 1 and 1, it will be 1. Okay, so here we have got that all the three inputs of these three T flip-flops are 1 and 1 and 1. So the next step will be the complement of this present state. So whenever we have 0, next will be 1. Whenever we have 1, it will be 0. Similarly for TB, okay, it is 1 and 1. Okay, so what will have? If it is 1 previous state, so next state will be 0. So it is previously 0, it is 1. For C also, similarly for C also, we'll have 1 and 0. That means if we now see the present state and next state, if we draw the state diagram of this unused state, what we'll see? Let us draw the state diagram. So what we'll have? If we have 0, 1, 0, here we have suppose 1, 0, 1. So for 0, 1, 0, the next state is 1, 0, 1. So that means from 0, 1, 0, it will go to 1, 0, 1 when the inputs are 1, 1 and 1. So when we have present state is 1, 0, 1, the next state will be 0, 1, 0. So from 1, 0, 1, it will go again back to 0, 1, 0. This means whenever we have 0, 1, 0, it will go to 1, 0, 1, and when we have 1, 0, 1, it will go to 0, 1, 0. This means whenever we have 0, 1, 0 as the present state, the next state is 1, 0, 1, and when we have this present state, the next state is this one. Again, it will go to this one, and from this state, and again from this state, it will go to this one state. Okay, that means if any one of these output is occurring, okay, at the counter output, what will happen? It will be repeating within themselves. So this problem is known as lockout condition or lockout problem. Now we can say that this counter output, whenever it has any one of these states, it will be locked within these two states. Now we have seen that this counter is locked between these two states, that is 0, 1, 0 and 1, 0, 1. Okay, this is the state diagram. If by any chance, if there is an output of 0, 1, 0 or 1, 0, 1, it will be locked. This counter output will be locked between these two states. So this is called as the lockout problem. Suppose we have 1, 0, 1 to 0, 1, 0 transition, and when we have 0, 1, 0 transition, it will go suppose to 1, 0, 0 transition. That means it will go to any one of these states. You can assume it to be 0 or you can assume it to be 1. It is up to you. Here I will consider that whenever we have 0, 1, 0 output, the next state output will be suppose 4. 4 means 1, 0, 0. Suppose to solve this problem, let us assume the following state diagram. Suppose whenever we have 1, 0, 1 at the output, it will go to next state 0, 1, 0 as previously. It will go to 0, 1, 0. And this is also a new state. Okay, so we have to go to some used state. And suppose I have considered here it to be 1, 0, 0, that is 4. Now if we have gone up to this used state, if by any noise signal or if any interference makes the output of this counter either of these two states, okay, either one of these two states, whenever it occurs the output is 0, 1, 0, it will go to 1, 0, 0, and whenever it occurs 1, 0, 1, it will go first to 0, 1, 0, and from 0, 1, 0 it will go to 1, 0, 0. That means now from unused states, these are the unused states, and it will go to this is used state. Now let us make the state table after correction. So here we'll have present state, here we have next state, and here we have the flip-flop inputs. So we'll make the complete table, okay, and we'll find out the respective equations. So present states will be similar to the previous table. Okay, so here we'll have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Except these two states, that is 2 and 5. Okay, so the remaining table will be similar. Okay, only now we have to fill up this table as per the assumed conditions. So these two row will be similar. Okay, so it will be 0, 0, 1, 0, 1, 1, and the inputs are 0, 0, 1, 0 1 0. Now for 0 1 0, what will be the next step? For 0 1 0, the next step is 1 0 0. For 0 1 0, the next step is 1 0 0. Now we have to find out the TA TB TC. This TA is from the equation we have, it is A XOR B, that is A XOR B. Okay, so what will happen? Okay, that means 0 and 1, it will be 1. So here we have 1 and 0, it will be 1, and here we have 0 and 0, it will be 0. Next we have this 0 1 1. So from 0 1 1, as per the given question, from 3 it will go to 7. So 1 1 1, and here we have already found out, that is 1 0 0. Here we have 1 0 0. So from 4 it will go to again 0. So it is 0 0 0. Except these 2 and this 5, all the remaining rows will be the same. So here we'll have 0 0 0. Here we'll have 1 0 0. So from this state diagram, here we can say that from 1 0 1 it will go to 0 1 0. Okay. So from 1 0 1 it will go to next state 0 1 0. So now 1 and 0, the TA value will be 1. So for 0 and 1 it will be 1, and for 1 and 0 it will be 1. Okay. Now here we'll have these remaining two rows will be the same. Okay, so here we'll have 1 0 0 1 1 0. Here also 0 1 0 and 0 0 1. Now we have made this state table with the assumed correction. Okay, this is the assumed correction. These are the two unused states. Whenever we have 0 1 0, it will go to 1 0 0, and whenever we have the unused state 1 0 1, it will go to 0 1 0 first, and from 0 1 0 it will go to 1 0 0. As per these conditions, we have changed this third row and this sixth row. Now we will find out the expression for TA, TB and TC, and from that we will draw the circuit design. Here we will find out K map for TA. So here also we will have a 3 variable map. Now here we have to fill up the modified TA values. Okay, previously we considered some don't care conditions, but here we have these corrected values, that is 0 0 1 1 1 1 0 0. So here we have 0 0 1 1 1 1 0 0. Okay, so this will be one term and this is the second term. So here we'll have TA is equal to, from this term we'll get, it is A B bar. Okay, plus from this term we'll get, it is A bar B. A bar B. Next we have K map for TB. Similarly for TB also we'll have a 3 variable map. So here we have to fill up with the TB values after correction. So after correction the TB values are 0 1 1 0 0 1 1 0. So here we'll have 0 1 1 0 0 1 1 0. So here we'll have this combination. So TB is equal to, so this is B bar C plus B C bar. Okay, so this is nothing but B XOR C. This is nothing but A XOR B. That is TA is equal to A XOR B, and similar to the previous case. Okay, and TB is equal to B XOR C. So these two TA and TB values are same. Now let us go for TC. K map for TC. Okay, so here also we'll have a 3 variable map. Okay, now we have to fill up this table with TC values from the modified table. So here we have 1 0 0 0, then 0 1 0 1, 1 0 0 0 0 1 0 1. Okay, so how we can combine? So this will be one combination and this one will be single combination. Okay, so TC is equal to, from this term we'll have AC plus from this term we'll have A bar B bar C bar, A bar B bar C bar. So now TC is modified to this equation. Previously we had TC is equal to A XNOR C. Now after self correction we will have this equation. Now we will draw the circuit design. Now here we will have 3 flip-flops, 1 flip-flop, 2 flip-flop and 3 flip-flop. And this is suppose A, this is B and this is C. Here we will have this TA, this is TB and this is TC. Let us connect this clock. So connect to a common clock source. Okay. So this is a synchronous counter. So here we'll apply a clock signal. Now TA is A XOR B. Okay. That means bring a line from here. Okay. From A. Bring a line from B. And do the XOR operation. Okay, that means here we'll have this is A XOR B, A XOR B. So this is connected to TA. Now we have TB expression. TB is B XOR C. This is B, this is C. So here we'll have one XOR gate again. Okay. So the inputs are B and C. So this one is B and take a connection from C. Okay, so B XOR C. So this output will be connected to this TB input. And next we have this TC. So take a line from A, multiply with C. Use an AND gate here. Okay, this is A line. Okay, here we'll have A, C. So we have to use here another AND gate. Oh sorry, this is A bar, B bar, C bar. So here we can see that for the third case we have A bar, B bar, C bar. Okay, so you have to give input, one input from C bar. Okay, second input from B bar. So take a line from here and connect it to the input of this AND gate, and one input from this A bar. Okay, take a line from A bar and connect to the input port of this AND gate. Here we'll get A bar, B bar, C bar at this AND gate output. Now we have to add these two. So use a OR gate here. Okay, so this will be one input. Here we'll have A bar, B bar, C bar. At this AND gate output, this output will be input of this OR gate, and here we'll have this TC. Okay, so we have got the counter circuit. So this is the required circuit design as per the given conditions with self correction. So this is the solution of the problem number 6.24. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.